And we're back. Welcome back and happy Thursday. Today we will continue on with our discussion of the application layer, and our focus will be on a number of very popular network application types as well as domain name system, DNS, which is critical, absolutely critical to the functioning of the modern internet. But before we do that, some administrative bits. Homework number 1 is due this Friday at 10 a.m., the 5th of February. Please mark your calendar, your electronic device, your PDA, smartphones, what have you, that this is 10 a.m. and not 11:59 and 59 seconds. Okay, so today we'll continue on and we'll take a look at electronic mail, some other important applications, and DNS. So email, probably, certainly, definitely the first killer application that led to the proliferation of the internet. When email first came out, it was immensely useful and led in part to the spread of people using email. Now, in an email system, there are 3 major components. There's the so-called user agent, which is that piece of software that acts on your behalf, the user of email. There's the mail server, which talks to other mail servers to send and receive the email messages. And then there's SMTP, Simple Mail Transfer Protocol, which is the interaction between servers to transfer and deliver these messages, these emails. And so the user agent is your mail reader, and it's responsible for composing, editing, reading your mail messages. Now, certainly very popular today is webmail, but in the earlier days of email, the user agent would be a piece of software that you'd have to install on your machine. Now, popular user agents are things like Outlook, Thunderbird, iPhone Mail Client, and so forth. And the user agent handles the outgoing messages and the incoming messages on the server. It interacts with them on your behalf. Now, in this notation, we have a couple of things that are important to note. This green box, that's the so-called outgoing message queue. Messages, mail, electronic mail messages are deposited into the outgoing message queue, and it's from this outgoing message queue that an agent, your SMTP server process, wakes up, or more correctly, client process wakes up and delivers that email message. And the reason why it's a queue, because the user agents don't have to be connected to the mail server all the time. So you come along, you send your email, it gets dropped into the mail queue, outgoing message queue, and then the user agent goes away. You don't have to be connected actively for your message to be delivered. We also have a user mailbox, and user mailbox is a storage pool that's used to store all of the messages that are destined for you. And so when messages are delivered, you don't have to be attached. When you finally attach, you retrieve your messages from your user mailbox, just like a real mailbox, or more like a P.O. box if you think about it. The mail server then has this mailbox, has a message queue, but it also engages in this SMTP protocol. Now, this SMTP protocol is an interaction between a client and a server, where the client is that particular mail server that sends messages to another, and the server is that mail server which is the destination of those mail messages to which it's delivered. And so each mail server acts like a client and a server, so you could really call these mail peers instead of mail servers. Okay, so email uses the Reliable Transport Service, TCP, Transmission Control Protocol, because these messages need to be delivered without corruption and in the same order in which they were sent. Because if your email message gets dropped or bits change or data gets lost, it's no longer the same email message. And the mail servers transfer to one another directly. So there's a direct connection between the source mail server and the destination mail server associated with the recipient of that email. And so this transfer it proceeds in three phases. There's the handshaking, where they identify one another, the login, the greeting. Then there's a transfer of messages, and then there's the closing of the connection. And in the old days, or older days, when I talked about SMTP, I'd actually connect and show you in text what these messages look like, but email these days is more secure, and it's not possible to actually show it to you live in text. But nonetheless, it's a set of command and response-like interactions, just like we saw with the HTTP interaction when I did a telnet to the web server and typed in the GET request. And so these commands are ASCII text. These days it's encrypted, and in the earlier days it was 7-bit ASCII. And so a sample interaction is as follows. Suppose Alice is on one machine. Alice runs her user agent that connects to her mail server, and she composes a message, and that message is destined for username Bob at mailserver@someschool.edu. Now Alice's user agent then, after she composes her message, sends it to her mail server, and that message is placed into her mail server's outgoing message queue. Now, eventually, this SMTP process runs, and it picks up the message from the head of the queue and sends that message by opening a connection to Bob's email server at someschool.edu. So then, once that connection is established, that SMTP process on Alice's machine, Alice's mail server, sends Alice's message across the wire to Bob's mail server, and when it arrives, Bob's mail server looks at that message and says, hey, it's destined for username Bob. So it finds the mailbox associated with username Bob, and then it puts Bob's email message that it just got from Alice into Bob's mailbox, and then returns, and it closes the connection. And Bob, at some point, comes along later, runs his user agent, thinking, gosh, do I have any new messages? Bob's user agent connects to his mail server. He authenticates himself, accesses his mailbox. When he authenticates himself, the mail server does, and he downloads all of his messages. And Bob reads Alice's mailbox. So I'm not going to cover the interaction. Used to be able to do this about maybe 7 to 10 years ago, but that's not possible these days, and so I'll skip over that. So with SMTP, it uses persistent connections. An email message consists of multiple objects, and they're sent in the same transaction, the same connection. These multi-object, multi-part messages. And so your email could contain the text, some objects these days like rich text and other formatting information, pictures, attached documents, and so forth. Email has gotten a lot more sophisticated over the years. In the early days, email was just plain old text. And so it uses persistent connections, and these persistent connections stay up, and all of the messages are transferred across these persistent connections. You don't have a unique connection per email that's sent. It keeps this persistent connection. And so SMTP requires there to be a header portion that identifies things like the recipient, who composed the email, and so forth, as well as a body. And it uses very simple character turn line feeds to connote the end of the message, the delimiter of the message. And so when you compare SMTP to HTTP is a pull model. So the client opens a connection, sends a request, and pulls back the data to itself. In the case of SMTP, the client opens a connection to the other SMTP peer or server, and then it pushes that data in the form of the email messages. And they both have ASCII, encrypted ASCII these days, command response interactions. And so in HTTP, each object is encapsulated in its own response message, but SMTP, you have multiple objects that are sent in a so-called multi-part message. The message is comprised of multiple objects. All right, so we're not going to talk about the message format, but let's look at the so-called mail access protocol. Now that corresponds to how the user agent interacts with the email server to which it is attached, where the respective user's account lives. And so SMTP delivers the message to the user's mailbox, but then how does the user interface with his or her mailbox? And so the mail access protocol exists in three major flavors. There's POP, Post Office Protocol, and you've probably seen in your mail clients POP3, that's Post Office Protocol version 3. And there's another one called IMAP, Internet Mail Access Protocol. We'll talk about all these, and HTTP, or webmail. Now, webmail was a huge advance in that you do not need to reinstall the user agent software anytime you want to upgrade the capabilities of the mail client. All you do is just update the PHP, Node.js script on the server side, and then as the browser connects, you can change the interface completely. And so let's take a look at POP. Now, earlier POP versions used a download and delete mode. So you connected to your user agent, your POP3 user agent, to your mail server, connected to your mailbox, and it would download those messages, deleting them from the mail server, and a copy is maintained on your client. But this introduced a little bit of a problem, because if you read your email from different places, from maybe your home machine, your mobile phone, your laptop, or maybe at school, you'd have your email scattered among different machines, and you don't access a particular machine, you're not going to get access to those emails that were downloaded and deleted off the server. Newer versions or more current versions of POP3 allow you to do what's called download and keep. It downloads a copy of the message to the mailbox, and it's not unless you explicitly delete that message that it takes it or removes it from the server. It no longer exists. And so POP3 is also stateless across sessions. There's no state that's remembered where you left off. Let's take a look at IMAP, Internet Message Access Protocol, or IMAP. And in IMAP, all the messages are kept in one place at the server. That's in contrast to the first early versions of POP3. And this allows you to add other things like this notion of folders. And so IMAP's big breakthrough or big contribution was to allow you to create folders, and these folders are places or storage containers, if you will, in which you can place messages. So now, as the amount of email that someone received started to grow, it gave you the ability to organize it. And so it keeps this state across sessions. It remembers the names of the folders and which email messages are mapped to which folder. And so when you access IMAP, it's all kept at the server, again, until you explicitly delete something. So let's take a look at DNS, Domain Name Service. That's a really important application. And this particular application is a little bit different from other applications in that while it sits at the application layer, it runs and it does something, this application gives you information that's needed by the network layer. And so many times when you want to remember something, people have identifiers, like you have a passport number, social security number. But people are much better at remembering names for things. When we think about locating a host or machine on the internet, we uniquely identify it by that 32-bit number, the IP address. But that IP address is difficult for us to remember. So what we do is associate a name of our choosing, like desu.edu, ibm.com, bloomberg.com, gamestop.com, and so forth. We associate names with things because it's much more convenient and easier for us to remember things by their name. And so the question that is addressed by DNS is how you can map or associate a name with the underlying IP address. Because at the end of the day, all your browser cares about, all the TCP connection cares about, is the port number and the IP address at the end of the day when it goes to the network layer. But how do you map between this name, which is useful for us, like you type into your browser, www.disney.com, and this translation happens to give your client the IP address needed to make the connection. So that's the purpose of Domain Name System, or DNS. It's a distributed database, and in order to scale, it's implemented hierarchically. And so you have a bunch of name server processes running on different hosts scattered around the internet. And these name server processes, these DNS instances or these name servers, they interact with one another in a stylized hierarchical fashion. And this is how you get it to scale. Now, as I said before, it's an application layer protocol. it maps the host name, or the so-called domain name, to an IP address. And so it's core to the internet function. And the beauty of keeping domain name system as an application is that you can push this complexity at the edges of the network and continue to keep the network core very, very simple. If you can keep it simple, a few moving parts, you can make it very, very fast. And so what does DNS service do? It maps host names to IP address, so it provides a translation service. It allows you to alias host names. So maybe you connect to Amazon.com, you're really using a server in Amazon's East Coast data center, or if you live in Oregon, you're using an Amazon instance in its West Coast data center. But to you, you just use Amazon.com. You can use DNS services to map you to one of a number of different instances, but to you, it just looks like that high-level domain name, Amazon.com. You can also use it for mail server aliasing. You can connect to a mail server for example, Amazon.com, without changing the domain name, and DNS provides services for that. You can also do load distribution. You can have a number of different physical instances circle through DNS, and each time you access it, it's going to select from one of a number of instances, and that's a way of distributing the load for access to things like web servers to get scalability on the cheap. And so a question that one might ask, is it centralized? Well, absolutely not. If it were centralized, that would introduce a single point of failure, and if someone attacked that single point of failure, that DNS, you would bring down everyone's ability to map names to IP addresses and basically shut down internet access. And so that doesn't scale very well, and DNS exists in a hierarchy. At the top of the hierarchy, we have root DNS services. And these root DNS server instances talk to another level in the hierarchy, one for the .com names, one for the .org name, .edu, .me for some mobile, and .fr for France. And this second layer in the hierarchy are given a name. It's called top level domain, or TLD DNS servers. And so they divide the namespace for domain names based on the extension, and all of those with the .com or commercial extension are served in terms of the lookup, the translation between names and addresses by the .com top-level domain name server. And so the same is true for .org, .edu, .me, .net, and all of those domain name server extensions, those 3 digits, sometimes 2 digits at the end. And so what happens is, if, for example, you wanted the IP address in order to make a TCP connection to Amazon.com, what you do is your client first contacts the root server and says, hey, do you know the IP address for Amazon.com? So the root server says, hey, that Amazon.com ends in .com. And you notice each part of the domain name is separated by a dot. So it says, oh, you have a .com address. It's partitioned based on this extension here, .com. I don't know the mapping for the IP address corresponding to Amazon.com, but since you're .com, you need to contact this .com top-level domain name server, because there you'll find all of the name to address mappings for .com domain names. So then the client queries the .com DNS server, and it sees, oh, well, you want the Amazon.com. This .com DNS server says if you want all the Amazon IP to name mappings, you need to go to Amazon's authoritative DNS server. So on the bottom level of the hierarchy are the authoritative DNS servers. And so in this authoritative DNS server for Amazon.com, it has all the name IP address mappings for all of the machines that are owned by Amazon. And so once you contact that Amazon.com, it returns back the IP mapping. You get that, and you can now connect using that IP address. So the root name server is contacted by the local name server, and the local name server is that DNS server for that particular organization. And so if you're at Amazon.com, for example, this DNS server at Amazon is going to be the one that you contact locally. You never contact the root directly. and your local DNS server is going to initiate requests on your behalf. So the first thing that happens is the local can't resolve that name because it doesn't have that address mapping, and so it contacts the root name server, and the root name server says, oh, well, I don't know what that is. I don't have a mapping for it, so let me contact the authoritative name server. If it's not known, it gets the mapping, and then it returns it. And so a lot of these requests are forwarded around if they do not have the name to IP address mapping. And so if you look at the root name server, it's drawn as a single node in a hierarchy for DNS, but it's not implemented as a single node. It exists as a bunch of data centers that are scattered around the world. And this particular map shows you 13 of the root name servers worldwide. They're replicated many times in large data centers so they can scale to serve a lot of these root name server lookup requests. And so these TLD servers, they're responsible for groups of stylized domain name schemes. The .com, the orgs, the nets, the edus, arrows, jobs, everything. There are also top-level domain name servers, TLDs, for various countries like .fr for France, .ca for Canada, .uk for United Kingdom. And so there are different organizations that maintain the DNS servers for various parts of the domain name space. For example, Network Solutions in the DC area maintains the servers for the .com TLD. An organization called Educase maintains the DNS server TLD for DNS for the .edu. So desu.edu, the name server that maintains the EDUs is Educase. And so somewhere in Educase TLD for the EDUs, the authoritative is going to say, hey, if you want this mapping for www.desu.edu, you have to go to the authoritative server, DNS server for DSU, and that's somewhere, and that's sitting somewhere in Grossley Hall on campus. And so the authoritative DNS server is owned by the organization, and it is the authority that provides the ground truth mapping for what the equivalent IP address is associated with a domain name server. And so this authoritative DNS is maintained by the organization itself. And so DSU's IT organization is the one that maintains the authoritative for Delaware State University. And that's where you'll get, for example, College of Agriculture server domain names, or you'll get maybe the nursing department domain name and all the individual domain names for hosts across the campus. And so the local DNS server doesn't necessarily belong to the hierarchy. Each ISP has one, and that's called the default name server. So when you're in your house, you have a local domain for your house, and then when you go to look up an address, an IP address, your request for name to IP address resolution goes to the default name server associated with your ISP. And so that's local name server is the launching point for whenever you want to look up the IP address mapping associated with a domain name. And so whenever you as a host make a DNS query, like using nslookup command, that query is sent to the local DNS server. And that local DNS server maintains a cache, and in that cache is stored name to address mappings associated with name to address mappings that it has already resolved or obtained. Now, if it doesn't have that name to address mapping, that local DNS is going to act as a proxy, and it's going to forward your query into the hierarchy. So that's your entry point. You don't get to directly as an application. You don't get to query the DNS system. It's your local DNS that does this on your behalf. Now let's take a look at how the interactions are between the different DNS servers, whether it's the root, the TLD DNS servers are local, and the hosts. And there are two different schemes. One is called iterated query, and the other is called recursive query. And this example is iterated query. And so we have the requesting host, and let's say you're in computer and information sciences at poly.edu, and your host looks up gaia.cs.umass.edu as a domain name. So you do this, and it finds it doesn't have a mapping for gaia.cs.umass.edu in its local cache. So what does it do? It forwards that request to the root DNS server, gaia.cs.umass.edu. So the root server says, well, I don't have that mapping, but I know who does have that mapping. The top-level domain name server for all the EDUs managed by Educase, it has that mapping, and it will know what the IP address to name mapping is for Gaia.cs.umass.edu. More specifically, it's an EDU, so you need to go to the EDU TLD server. So the root DNS returns back a forwarding address to the local DNS server, and now the local DNS server acting on your behalf, it goes to that TLD for the EDUs managed by Educase, and it says, hey, do you know the mapping for Gaia.cs.umass.edu? Now, this TLD DNS server, it says, well, I don't know what this mapping is, but that's a umass.edu, and I know the address of umass.edu's authoritative. So the TLD DNS server for the EDUs returns back a forwarding address to the local DNS server, and then that local DNS server goes and contacts the authoritative for umass.edu. So it contacts umass.edu and says, hey, do you know the IP address for Gaia.cs.umass.edu? It says, yes, I have all of the mappings for every host that's inside of umass.edu, all the umass.edu domain names. And here's the IP address. I'm going to return it back to you, local DNS server. So now this local DNS server, it takes this name to address mapping for Gaia.cs.umass.edu that it got from the authoritative for umass.edu, and then it stores it locally as a cache entry so that any subsequent name address resolutions that come in from its local network are going to be resolved instead of being circulated through the hierarchy. And so after doing this caching of that mapping between Gaia.cs.umass.edu and its IP address, it's going to return that mapping back to the requesting host. So the requesting host has the corresponding IP address. It then uses that to initiate a connection. Okay, so that's our iterated query. Let's contrast that with recursive query. Now, in each of the case for iterative, when the local DNS got back a response, it was a forwarding address, and the local DNS did that work itself in contacting whomever it believed had the right mapping. And so the local DNS did all the work. Now, in recursive query, that's not the case. The DNS that receives the query, if it does not have the name address resolution, it forwards it on to the next one instead of saying, hey, here's a forwarding address, you go and you do the work. And so the burden of name resolution is on the server that's contacted, right? And this can introduce a heavy load at the upper layers because if you have all this forwarding circulating through that one route, that's going to constitute a heavy load because that's not the only resolution out there on the internet. There are many of them. Anytime you need to make a connection, someone types any domain name in their browser, it's going to do a query before it actually initiates the connection. So that being said, the requesting host on poly.edu, it goes ahead and requests Gaia.cs.umass.edu. So that first edge is that name address resolution request that goes to the local DNS server. And let's assume that it did not have a cache entry. And this is just starting in Bootstrap, and there was no cache entry that was at this moment stored in a local DNS server. And so the local DNS server says, well, I don't have a name address mapping for Gaia.cs.umass.edu. So what does it do? It forwards it to the root DNS server, and that's the second edge. And once it forwards it to the root DNS server says Gaia.cs.umass.edu. That ends in edu, so it's got to be the edu top-level domain name server. I don't have the mapping, but I know where the mapping is. Let me get it for you. And so this root DNS server sends a message for the name address resolution from the TLD server for all of the edu domain names. And so that TLD DNS for the edu says that's a UMass edu. I don't have that mapping for Gaia.cs.umass.edu, but I know who does. Let me go get it for you. And so that TLD server for the EDUs, managed by Educase, sends a request message to the authoritative for UMass edu, the DNS server, and it looks it up and it says, oh, I have the mapping. This is the IP address. So it returns it back to the TLD DNS for the EDUs, which then returns that back to the root, which then returns that back to the local DNS, which then caches a copy and then sends that answer back to you, and you get the IP address mapping, you get the IP address, and you initiate your connection. Now, at any step along the way, any of the DNSs could theoretically cache that entry, and that would save you a lot of messages on subsequent name address resolution request. But it's very typical to only have the local DNS server do that caching. But theoretically, you could do that anywhere. It's not efficient to do that because with the number of queries happen at the root, it's not efficient to do that because you'll fill up a lot of storage with all those cached entries. Okay, so once the name server learns a mapping, it caches it. Once it receives it, and that cache has a timeout entry, and that cache entry will disappear based on a field called a time to live. And so the TLD servers are typically cached in local name servers to avoid that traffic going through the root. And so in the case of recursive query, if you're caching the TLD in local, you never pay the cost of traversing through this root DNS. And likewise for iterative query, if you cache the TLD in the local, you never pay the cost of this interaction edge 2 and response 3 with the root DNS server. And so what that caching of the TLD inside of the local server, DNS server, does is it saves a lot of traffic from the root server, and so the root name server is not very often visited. And cache entries might be out of date. If, for example, host name changes its IP address, it might not be known internet-wide until all of these cached records expire. So a record can get stale, and it goes away if it gets stale, requiring a new lookup. But if you change, you have to make sure that the timeout occurs. Otherwise, anyone who does a resolution will still understand the old name IP address mapping. And so what are these records? These are called resource records, and these resource records are the unit that is stored in the DNS servers. And so these resource record formats include, like I said earlier, this time to live field, and the TTL fields are used to determine how valid or when these things, what is the expiration date, how long they stay valid. And then we have the type name. The type field, rather, determines what kind of resource record it is, and depending on what type of resource record it is, the name field and the value field are interpreted differently. And so there are 4 different types. A type A, or authoritative resource record, is this name to IP address mapping. It's the ground truth IP address associated with the domain name. And so a resource record with a type field of A is called a type A resource record entry in a DNS. All right. And so a type NS is used for your name server. And if you have a type field of NS, the name field is interpreted as the domain, and the value is the host name of the authoritative name server for that domain. And so what this NS says is if you want to access anything in domain foo.com, for example, this is the domain name of the host you're going to use to resolve those records. And so it tells you who is the authoritative. Now, of course, just because you have the NS record, it doesn't mean you know the IP address to contact the authoritative. You have to contact the authoritative and get this IP address from someplace. Okay. So then we also have a CNAME resource record. If the type field is CNAME stands for canonical name, and that's how you can get aliases. And so in the example in the book, if you have IBM.com, well, when you try to connect to IBM.com, IBM.com is your name, but the value is really server east back up to IBM.com. And so the value is the so-called canonical name. And this is how you get aliases, how you have multiple things that look like IBM.com, but you really have a particular instance that you can connect to. And then for mail server, it's a type MX type name or type field is value MX. The value in that case for an MX resource record is the name of the mail server associated with the domain name. And so you have domain name IBM.com. The mail server is mail1eastcoast.ibm.com, for example. Okay. And so this is a schema of what the query and reply message looks like. And so here you have a message header, and that message header identifies whether it's a query or if it's a reply. So the query is the give me the mapping. The reply contains all of the matches to that query. So it's almost like a database lookup, but it's done over the internet using these messages that go back and forth. using these packets. And so we have some flag fields, and these flags tell you if it's a query or a reply, if you want to use recursion, if recursion is even available, and if it's an authoritative reply, meaning does the reply come from an authoritative server, meaning is this name IP address mapping not a cached one, but the one that is from the owner of these name IP address mappings. And so we have these fields, and then we also have our questions. These are the variables saying the name is equal to IBM.com, for example. And we have a field for the answers, which are the replies to these questions. And then we have some variable number of authoritative stuff as well as other information. And in fact, if you go into Wireshark and you turn it on and you go to a new website, you'll actually see these DNS queries swirling back and forth across the internet. Okay, so how do you get new records into DNS? Let's say you have a new startup called Network Utopia, and you want to grab your internet real estate. You're going to go to a domain name registrar, for example, like Network Solutions, Namecheap, all sorts of them, GoDaddy, what have you. And you're going to say, okay, well, I want networkutopia.com. Okay, so you pay the subscription fee to own that domain name, and it's yours. And then what this Network Solutions does, it provides names and IP addresses of the authoritative name server that's going to be used to map between your networkutopia.com and an IP address. And so the name service registrar are going to insert two resource records into the top level domain name server for the .coms if you're registering networkutopia.com. And so one of them is going to be the name server record. That's going to be for all domain names networkutopia.com. You're going to contact a DNS server called dns1.networkutopia.com. So this says, what is the name server that I'm going to use to look up addresses for any domain name that is ending in networkutopia.com. Okay. So then the other record is the authoritative record. Now that you know for any domain name that ends in networkutopia.com, use that DNS server. Well, what's the IP address of the DNS server? We need the authoritative record, and that's the other record. And you'll notice this authoritative record, well, the name field is the host name for the DNS, and then the value is the IP address, and it's a type A resource record. And so you create the authoritative server type A record for networkutopia.com, and you could also additionally create others like the mail server record for networkutopia.com. And so your domain name registrar is the one that pushes these entries into the TLD server so that the world will know ultimately where to go to look up name, address, IP mappings for your domain. All right. So DNS servers are targets that people try to attack to disrupt use of internet resources. Because if you can't map between names and addresses, you can't connect unless you have memorized the IP address, provided the IP address stays fixed. And so what one could do is many things to try to prevent or deny people the ability to connect to internet resources. You can bombard the root servers with traffic. Now, that's not very successful and hasn't been to date. They're fairly beefy, and a lot of cached records get put in local DNS servers that completely avoid contacting the root server. But you could try. You could try to bombard the TLD servers, and that could be more dangerous. Yeah, that's true. There are other technologies called Cloudflare that try to do automatic elastic scaling for DNSs. And so these days, people are pretty good in trying to prevent DDoS attacks that target DNS services for TLD as well as the root. You could also try to redirect. If somebody tries to resolve a name and address, you could intercept that DNS query and then respond as if you were the DNS. All right, so if you're intercepting queries, well, then you could sit in the middle and then try to do interesting things with the traffic and deny them access. So now, as the man in the middle, you intercept them, and then when they try to connect, you control what it is they're trying to do. There's DNS poisoning. You could try to send bogus replies and in effect, in doing so, populate all of those local DNS caches with false entries, and in doing so, deny someone the ability to access web resources. You could also exploit DNS for DDoS. you can send queries that spoof the source address and the target IP, right? And this requires you to do a lot of things to amplify, so respond to a lot of queries and insert yourself in the middle. So there's lots of things you can do, but people as of late have gotten pretty good in trying to protect and circumvent these types of denial of service attacks, where you try to hack or disrupt, rather, the DNS queries and responses. So that's all I have for today. That's DNS, and we will end there. And again, please make sure you're working on the homework. It is due tomorrow. And as usual, please stay healthy, please stay safe, and I will see you all on Tuesday.